Hi, everybody. This is Jani Radebaugh. I am so excited to be with you today and to be talking to you. I wish I were there with you in person, but one day we'll have a big party and I will be so excited to meet you. But I want to talk to you today about a couple of really exciting things. Mostly I'm going to talk to you about something I'm involved in that just happened this past year, and that is the very exciting Dragonfly mission to Saturn's moon Titan. This is the next New Frontiers mission in NASA's quiver. It was just chosen last July, and I am on the mission team, and I am so excited about that. I'm gonna make this a little bigger so you can see me better. Okay. It is really spectacular, really fascinating, and I have so much to tell you about concerning that. But first, I actually want to talk about something else that I've been able to do. And the reason I'm thinking about this a lot is just because of the very interesting times that we live in now. And I'm thinking about how I cope on a daily basis with these very significant changes in ways that draw on the skills I learned going down to the bottom of the world to search for meteorites. I must really like this because I've been 4 times and I'm not done yet. I really want to go back, and it's one of the most spectacular experiences I've ever had in my life. It's a chance to go and pick up pieces from outer space that are just sitting out there on the ice. You just drive a snowmobile right up to them and pick them up and put them in a bag and send them off to NASA. And we just, every time we see one, we just are delighted and just kind of can't believe it. But we end up finding hundreds every season. And the reason why is a subject for a different talk. But I do just want to mention that there's a lot of time spent waiting when we're doing this. We wait to get ourselves to New Zealand. We wait to go from New Zealand to McMurdo Station, which is the main US base in Antarctica. And then even when we get to McMurdo, we wait to get out into the field. And sometimes we wait for weeks. Sometimes it's a month that we wait in McMurdo before we can get out into the field. And it's frustrating, but at the same time, I pinch myself and I try to remember that I'm in Antarctica, and that's a real just benefit to doing this entire thing. And so I spend time going around and walking up to the tops of mountains, and here is Manavie looking out over McMurdo Sound. And this is the view that many of the early explorers had during the heroic age, the early 1900s. And here's a cross erected as a memorial to those explorers. And so sometimes we really feel like they did, although our waiting is nothing compared to what theirs was like. I believe this is Shackleton's expedition and the tremendous amount of waiting they had to do on that trip. But we still find things to entertain ourselves when we're out there. You know, I ride a fat tire bike out to the runway, and I probably never would do that in normal circumstances, but I had the time, and so I took advantage of that opportunity. And then once we get out into the field, we're still waiting. We're waiting to kind of get things unloaded. We're waiting to get it set up. Do we have all of our ski-doos? Do we have all of our field party members? Sometimes we're waiting in the field until they come. But we're so grateful to be there, and it's so beautiful. We spend up to 6 weeks in the field in tents and go out every day on snowmobiles and look for meteorites. Even when we're searching, there's a certain amount of waiting. You just look at our attitude here. We're just kind of hanging out. We're just waiting. I love this one right here of Manavie. She's just reclining, and you think, oh, that looks pretty nice. But if you look down near the bottom of the skis, you can see a lot of snow blowing. And this is starting at 0 degrees, and then the wind blows. And so it is 0 Fahrenheit. So it is always cold there. And we get used to it. We know that that's what it's going to be like when we're out. And then there are the days that we spend in the tents, and it's up to 1/3 of the time that we have in the field, we're in the tent and we're waiting for the weather. When the wind blows, it's picking snow up everywhere. We're huddled around an anemometer to see just how fast the wind is blowing here. and then we can calculate the wind chill. But of course we can't go out and search during these times, so we just sit and we wait in the tent. And while we do, we cook some beautiful stews, and we write in our notebooks, and we do little craft projects. And I kind of dive into those recesses of my brain that I don't normally get to access. And that is a real privilege. And I'm trying to remember that right now. I'm trying to remember that I can take some time to do things that I wouldn't normally. And I hope I'm taking advantage of that. We should remember that the Apollo astronauts also did a certain amount of quarantining. You know, they had these spectacular days in the field, up to 3 days on the moon. And then when they came back, they couldn't, you know, run to the arms of their loved ones or go out and talk about everything to the public. They had to sit in quarantine for 2 weeks because we didn't know what to expect out there in space. And so they complied with that, and just like they did with everything else, and learned how to wait themselves. So in many ways, I feel right now like Luke Skywalker. Always comparing my life to Luke Skywalker. I feel like, gosh, I'm just sitting there. I really want to go out somewhere to those remote corners of the galaxy and explore and do those remarkable things. But I need to be home for a while, just like all the rest of us. And so I'm trying to make the most of it. But let's get back to what you want to hear about today, and that is this amazing, spectacular Dragonfly mission. The video you're seeing might be a little slow and jerky just because it's through Zoom, and it's also kind of big on my PowerPoint. But what you should be seeing, I hope, and I'll send you a link later, you can go look it up, is Dragonfly descends down through the atmosphere of Titan. It gets released from its descent probe, and it just fires up and flies. It flies across the surface. It's got 4 sets of 2 blades all around the body. It's a drone quadcopter. Rotorcraft Lander is what we're calling it. It turns up an antenna, it communicates directly to Earth, samples the surface materials, and then picks itself up and flies again to the next destination. And it's really amazing. The time is now for us to be able to do this kind of a mission. It's taking our landed spacecraft one step farther, and really learning tremendous amount about the surface of Titan. So we all got together in September this last year after the mission announcement, and we probably look a little wide-eyed. We're all still kind of pinching ourselves, and we all look just remarkably kind of young. We're bright-eyed and bushy-tailed. That's not going to be true when we get there because we're going to the outer solar system, and so there's still a lot of waiting ahead. And I always wonder why are the Cassini team members so old? And well, it's because they've been working on this mission for as long as I will have been when Dragonfly gets there. But it's a great team. We're really excited. We have a wonderful PI, principal investigator. This is Zibby Turtle, and she's at the Johns Hopkins University Applied Physics Laboratory, which is where we had this meeting. What is it about Titan that makes this such a good opportunity? And really it's that we do not know how life came to form on the Earth, and we can't go back to study our own history. And let's all remember that the only place we've seen in the universe with life is planet Earth. It's almost certainly out there somewhere, but we haven't seen it. We've only seen life on Earth. And so we are groping around in the dark trying to figure out how are we going to recognize this when we see it on other bodies. And the best way we can think of is, well, let's think about what things were like on Earth and maybe look at the early days of Earth when life was just getting started. And so we look at these places in our solar system that might help remind us of early Earth. And it turns out that Titan is most like our planet in those early days, and it might hold the keys to understanding the origins of life. Here's a picture of Titan. This is the 4th one over that you can see in this image, and compared to the others at the right scale. Notice we've got very big Venus and Earth, and then about half that size is Mars, and Titan is just a little bit smaller. It's actually bigger than the planet Mercury, and it has a thick, dense atmosphere. It turns out it is the second densest atmosphere in the solar system compared to, or next to Venus. It has even more density than Earth's does, and it actually has about 1.5 times the surface pressure of Earth's atmosphere. And so it's really an interesting body. And not only that, its atmosphere is made mostly of nitrogen, just like Earth's. And the rest of it has methane, and then a whole compendium of organic hazes. And by organic, we mean made of carbon and hydrogen, sometimes some nitrogen, but it is not necessarily made by life. It's just the same kind of materials that are used by life. And Voyager noticed this when it flew by in the early 1980s. And then we've been watching that ever since. And so it's been a really compelling, really exciting place for us to study. We've also learned that like the other icy satellites that all exist from Jupiter on out, it is made mostly, well, about half water ice, and then the rest is rock and metal. And so that means the crust, the rocks, the lithosphere are all made of water ice. And that is a rock at Titan's location in the solar system. It's very cold there, about 90 degrees above absolute zero. And then deep down in the interior, as you go down, you increase the pressure on that ice and eventually it will melt. And there is an ocean of liquid water. And so just like the other icy objects in that part of the solar system, it is an ocean world. And this access to water is really exciting for us because, again, water is really important in terms of life in the way that we understand it. And so we're kind of following the water. We're looking for places where water is and just see if maybe the basic ingredients for life also exist and if life was able to start there. And finally, deep down in the interior, there are silicates and rocks, just like it'd be like the core of the moon draped in a mantle of water and ice. So we visited Titan with some other missions, especially the Cassini-Huygens mission. And here you can see it's gigantic. It's the size of a school bus. And you see the Huygens portion, which is by the European Space Agency on the right-hand side. This is tacked onto the side of Cassini and then was released down into the atmosphere of Titan. And no presentation is complete without a rocket launch. So hopefully you can see this right here.
7, 6,
take a drink while we're waiting.
5, 4, 3, 2, 1, and liftoff of the Cassini spacecraft on a 30-mile trek to Saturn. The program is in. Roll program is in. We have 3 hours. The spacecraft is on its way to Saturn. Sequence 20 seconds. Systems are go.
Okay, those of you with the sharp ears know that that's from the abyss. But I think it's so special that this could launch at night and got to go up through a cloud and kind of light it up like a lantern. It's a really beautiful launch. This was before my time. I actually wasn't aware of Cassini, so I didn't get to see the launch. But it happened in 1997, and finally it arrived at the Saturn system in 2004. And I love this image of Saturn taken from behind it. Basically, you know you're in a spacecraft because the sun is on the other side and illuminating the rings, illuminating the atmosphere. And this image mosaic from Cassini can show that really clearly. And if you look kind of off in the corner of the rings here, up in the upper left, I don't know if you can see my cursor here, but if we zoom in on that, it is actually the Earth and the Moon. And that helps to kind of place us in the solar system and let us know just how far away from home we really are. The other moons of Saturn are also really exciting, and they have a lot of lessons for us in the solar system. One of the most interesting was Enceladus, gushing geysers of water out into space. And my artist friend, Mike Carroll, I'm sorry, I don't have an image credit on here for him. Mike Carroll painted this for me. He took my image that I took in Antarctica. This is my teammate Minako carrying my computer case, and put me on the surface of Enceladus. And sure, I would love to sometime. I hope that can work out. And so as we arrived at Titan, the Huygens probe was released and descended down through the atmosphere and landed on the surface. And it actually landed in a kind of dry, dusty riverbed. That's the middle image that you see here. Do you see the rounded rocks kind of rolled around in the bottom of a river? The rocks have got to be made of either water ice or organic materials. Again, they're not silicate rocks like we're used to on the Earth. And there's a picture of the Apollo astronaut footprint just for you to kind of get a sense of scale. And as we were descending, we noticed a myriad of river channels, these dendritic networks, really well developed, that tell us that there is rainfall and erosion on the surface today. And this is from methane rain. It's so cold at Titan that methane is a liquid, and it forms the liquid that rains onto the surface and fills up lakes and seas. And so we're starting to think that, you know, hey, the materials are all different, but the landscapes and processes are the same. And so we can use Earth's landscapes that are similar to these to help us better understand what's going on Titan. And here's a picture of another really interesting landform. This is a lake or a sea called Ligeia Mare on the surface of Titan. And we're looking at a radar image, and radar records things that are flat, extremely flat as dark. And so all the dark features here we think are just really flat liquid. And it's liquid methane that's filled up the rivers that are feeding into that lake and the lake itself. And in this radar image, we can actually see an impact crater. This feature, there are impact craters on Titan, but not very many because the surface is pretty young. It's been erased by erosion and tectonism, maybe some volcanism. But this, you can see the bright rim, kind of half of it all the way around here. It's about 450 kilometers in diameter. And this middle peak ring, and these are all just rugged mountains that have been eroded by methane rainfall since then. And the exciting thing about an impact crater is that the impactor smashes into the surface, which is water ice. It would melt that water ice and it would pond up in this area that you can see is relatively kind of low-lying and flat, and this would have been a big melt sheet of water. And that could have interacted with the organics that are on the surface. Some of them we can see here in these dark stripes. You see these dark stripes everywhere. In other regions we can see them too, and it turns out they are sand dunes. Hundreds of thousands of sand dunes all across the surface of Titan. And the reason they're dark in this radar picture is that the grains are really fine. They're a sand, but instead of like a silicate sand like we're used to on Earth, like quartz, this is organic sand. And these organics come from up high in the atmosphere where the methane is broken up, it recombines into the organics, and they settle down to the surface where they are blown into sand dunes. And it could be there are some intermediate steps, like there's erosion of some organic layers, creating those big cobbles you saw in the riverbed for Huygens, and maybe creating finer and finer particles, these sands that get blown into sand dunes. And that was a real mystery. We kind of thought, yeah, how could we have sand dunes all over Titan? We didn't even predict that. And here you can see in an infrared camera, the visual and infrared mapping spectrometer shows as brown in this particular image stretch where the sand dunes are, and they're all found in the equatorial regions of Titan, with the exception of the upper right corner, which is a bright blue water ice continent called Xanadu. And nothing encroaches upon Xanadu, but otherwise we find the dunes everywhere. And as we look closely at them, we realize that in size and shape and behavior around topographic obstacles, they are exactly like the sand dunes in the big deserts of Earth, like these here in Libya. So in the Sahara, in Arabia, in Southwest Africa, and Australia, we find this kind of sand dune. And so we have determined to go out and study these sand dunes in as many locations as we can. And here we are in Namibia, in Southwest Africa. We've just dragged a ground penetrating radar instrument up to the top of the sand dune. It's taken us a couple of hours, and then we'll go back down the other side. And we're coming up with an interior structure of the dune from this radar, this ground penetrating radar, that helps us understand which way is the dune moving over time, which way are the sands moving, and then we can apply those findings to Titan. In the United Arab Emirates, we find a really unique condition, and that is that in the interdunes, the area between the dunes, there are actually liquids. And these liquids are not all that friendly. They're very salt rich, and yet you can see some regularly spaced mounds in the background. Those are algal mats, and the algal mats form even in the salty waters in these hyperarid conditions. And so we wonder if we could find, maybe some liquid methane in between our big sand dunes, and that might form an area that is conducive to life. Okay, we have some other features on Titan that are really interesting. If this is almost inscrutable. This is a really strange image, but you can see some mountains that have been eroded. And if you look in the right, kind of the upper right and the lower right, you can see some parallel straight features. And this isn't an image artifact. These are real. These are actually exist in the landscape. What would make something so straight and parallel? And we actually see similar features on Mars. And this is a much more close-up image of landscapes on Mars. You can tell now that these are ridges, and the ridges on Mars are carved by wind. Where would we be able to have wind-carved ridges? And it's in areas where there's just not much involvement by water, because eventually water will overcome everything and make it into a river channel that meanders across the landscape. But if there's no water, there's no rain, then the wind takes over and it carves everything into these long ridges called Yardangs. And this word comes from China and that region, kind of the Western Turkmenish region of the world, where there are a lot of Yardangs. And there are some in Argentina in the high kind of Altiplano Puna region. And we visited this area many times. You can see us kind of in the lower right corner here. And there are these big isolated towers that are being kind of destroyed by a couple of different wind directions, and big gravels are sweeping through the corridors. These features in Argentina are forming in soft volcanic ash, and here I am right in between a couple of them. And normally these layers in the ash would extend all the way across, but the wind is whipping right through and it has carved a corridor in between. And as it does that, it actually leaves behind some resistant materials, like there are these little cobbles poking out here. They make dados, or fingers, pointing into the wind. And here my student Jonathan is studying the orientation of all the dados so that we can put them into a wind model so that we can better understand what the winds are doing around the Yardangs in order to sculpt them and form them. And my student Dylan is working on looking at the hardness of the Yardang rock so that we understand what is the range of hardness that we can have to form a Yardang, and then we can relate that to the kind of materials we find on Mars and on Titan. We really love being there. It's such a beautiful landscape. It's very high. I always have to practice being at that high altitude and manage that. And it's very dry, but it is spectacularly beautiful. And right now NASA is paying us to go out and try to figure out these landscapes. We're making real progress. We've also been to some Yardangs in China. Here are our two guides that drove us out. You can see they're in some stacked lake bed clays, and you can see those regular kind of stripe shapes as we go off into the distance. And another artist friend of mine, Bill Dunford, placed me right on the surface of Titan studying these Yardangs. So maybe one day I get to do that too. Okay, well, so let's talk a little bit more about Titan and about why it's so interesting and a place that we'd want to send $1 billion mission to. And basically, it has got the key ingredients for life. So there's sunlight, and that sunlight comes and breaks apart methane and other molecules and allows that to recombine into long-chain organics. And those organics will sit up in the atmosphere. They will come down and form a haze a little bit lower in the atmosphere, and ultimately settle to the surface, maybe form layers, and those layers get eroded into organic sedimentary rocks and particles and sands all across the surface. And then also we have liquid water, and this is because the crust is made of liquid water, and if an impactor comes in and smashes into that crust, it will melt it and bring liquid water to the surface to interact with organics. Or we might even have cryovolcanism, liquid water that's coming up from deep in the interior and arriving at the surface. And so we've got that key fluid, but not only do we have water, we have a second fluid available, and that's methane. And the methane makes clouds and rain and rivers and lakes all across the surface of Titan. And it could be that methane could actually substitute for water in many of these critical life-forming processes. So really, only on Titan can we study this full range of the prebiotic chemistry that is possible leading up to the advent of life. And not only that, we can go to a lot of different areas all across the surface using our rotorcraft, and thereby being able to sample all of these really critical regions. And now is the time for this. We really have improved in our drone technology that we're ready to send something out to outer space. And Titan is really easy to fly in. It's actually 4 times denser than Earth's. Remember, it's 1.5 times the pressure, but because of the low gravity that you can see here, and it makes the atmosphere very extended, and so it's much more dense at the surface. And the low gravity also reduces the amount of power we need. So it's the perfect place to fly. And it turns out that this thing is actually really big. So I'm holding one blade right here, and there are 2 blades on either side of each of these rotors. So there's 16 total blades all the way across this aircraft. So, I mean, it's as tall as I am, it's a couple of me wide, and is really a spectacular machine. It's gonna fly directly there, and just remember from the video, it will just open that shell and drop and just start flying. And so that minimizes all of the things that we need. There's not gonna be an orbiter. We communicate direct to Earth and simplify things that way. It's going to take a while to get out there. So once again, we're going to be very used to waiting. We're going to launch in 2026 and arrive at Titan in 2034. But there will be a lot of things to do during that time, some testing and preparation, operations that we'll get all ready. And I hope we'll be going out and visiting landscapes that will prepare us for what we'll see on Titan. The first place we land is going to be perfect in terms of having all the things that we want. There are big sand dunes there, and so that's access to organics and these dunes and interdunes that we've been talking about. And here's a picture of us visiting the interdunes of Namibia. And you can see the really big kind of orange sand dunes pouring off into a river valley. And the interdunes between them are quite different. So we're continuing to, we'll be able to see that difference on Titan. What are the interdune areas like compared to the dunes? And we really hope there will be some liquids in some of those areas. And not only that, we're going to land kind of next to an impact crater. And that's all the bright regions that you see here. That's the ejecta blanket around this impact crater. And that means that there should be some liquid water that has interacted with organics on the surface. And we can see what those interactions may have produced. We can actually operate on the surface for more than 2.5 years, which is so exciting. In between each flight, there might be tens of kilometers. And so we can go a total of a couple hundred kilometers over its lifetime. It's really taking the kind of rover idea of surface exploration to a whole different level. And we'll just be able to understand Titan like we never have before. We're going to have a really interesting leapfrog strategy to be able to explore these areas. So we'll have a kind of safety base where we first land. And from there, we'll go out and overfly an area and then come back and land. And we can take a while to analyze that area. We'll spend most of the time on the ground, and then we can decide where the best next place is to go and land. And while we're on the surface, we're actually going to be making a tremendous amount of measurements in situ. We have a lot of really great instruments. The first is the mass spectrometer. And this Draco drill is actually going to drill into the surface through the legs right there and suck materials up into this mass spectrometer to be able to analyze them in situ. And then there is these two dots, the forward-looking gamma ray and neutron spectrometer, which will fire particles at the surface and help us understand the surface makeup kind of remotely. And then we also have a meteorology package that helps us understand pressure and temperature and wind speed. And we also will lower a seismometer from the Japanese Space Agency onto the surface and get a good sense of what's going on in the interior of Titan. And finally, we've got cameras upon cameras. We will have cameras for the flight, cameras for the ground, and really be able to characterize the area that we're looking at all across the surface of Titan in very great detail. This mass spectrometer will give us a huge amount of resolution on the makeup of the different particles we're looking at. And here you can see heavier and heavier particles that we'll be able to detect. And we'll use a couple of different methods. There's that laser desorption mass spectrometry, is kind of a broad survey of what things are. And then this gas chromatography can tell us specifically what molecules are there, and will even give us a sense of chirality. And you remember hearing about that. That's sort of a handedness of organic molecules. And life on Earth prefers a certain handedness. And so wherever we see an abundance of that handedness, we know something has organized it into that. And so we'll look for that on Titan. Is there 50-50 chirality, or is there a preferred chirality that might indicate that life or something is organizing that on the surface? What I'm most excited about, though, is just to look at the landscapes in great detail and better understand what we're seeing, both from the air. We can see the ripples on the dunes and understand that they're actively moving, and see the crest lines, their orientation to tell us the wind direction. We can see on the surface what's the difference between the dunes and the interdunes, and we can even get up to this microscopic scale. And that middle image that you can see is from the Bagnall Dunes on Mars, from the Curiosity rover. And when I first saw that, I think I gasped. I was just floored that we could actually get a handful of sand on another planet, because sand tells us everything. It's kind of the end result of all the processes in the area. It tells us materials available, what's happened to them over time. And so what I'm dying to get is that handful of sand on Titan, and it sounds like I'm going to get it. So in conclusion, for this mission, really Titan is just offering us the next step to answer these fundamental questions, which is, what makes a planet habitable? What chemical processes led to the development of life, and has life developed elsewhere in our solar system? and Dragonfly will be able to answer all those questions. And here's a little bit more about Dragonfly. You can even just Google Dragonfly Titan and it will bring up that Johns Hopkins University Applied Physics Lab website, and you can get to all those videos that I showed you before. So thank you so much for coming on this little journey with me, and for watching. Thank you for being fans of NEAF and for helping them out at this time, and also thank you to NEAF for bringing us all here and helping us be able to communicate with each other. It's really an amazing opportunity. Once again, I look forward to meeting you in person. I look forward to keeping up with you about Dragonfly and about all the exciting things that we're doing. And everybody stay safe, stay healthy, and keep looking up at the skies. The skies are still there for us to look at and enjoy every night. And if we do that, we can kind of keep ourselves sane, I think. So, all right, I will talk to all of you soon. Thank you so much for watching. See you later. Bye.